Welcome to this explainer. Today, we are diving into a really fascinating open secret in physics. We're going to explore how general relativity, Albert Einstein's towering achievement and frankly, an incredibly successful theory of gravity, is secretly hiding some massive foundational cracks. Okay, let's jump right in with a genuinely mind-bending paradox. General relativity is arguably the best-tested physical theory humanity has ever produced. But built right into the math of this brilliant framework is the inescapable prediction of its own eventual destruction. It is quite literally doomed to fail. There's this brilliant quote from our sources that perfectly illustrates how we should be thinking about this. They point out that general relativity has passed every single direct experimental test for over a century. Yet the theory is not a finished cathedral. It has structural cracks running deep through its foundations. So we really need to look at it not as a flawless masterpiece, but as an incomplete, effective theory, one that works perfectly right up until the moment it shatters. So here is our roadmap for today's structural inspection. We'll kick things off with the paradox of perfection. Then we'll unpack the major fault lines, singularities, vacuum energy, missing mass, and the quantum mechanics clash. And finally, we'll look at how brand new experiments are probing those very edges. All right, section 1, the paradox of perfection. Before we break this theory down, we really have to understand the unbelievable century of triumphs it's achieved. Let's just quickly trace how these undeniable successes built up over time. In November 1915, Einstein published his compact equations declaring that mass and energy curve spacetime. Boom! By 1919, during a solar eclipse, astronomers measured starlight physically bending around the sun, confirming his theory over Newton's. Fast forward to 2015, and LIGO detects the literal ripples in spacetime from colliding black holes. And then in 2019, the Event Horizon Telescope captures the actual shadow of a supermassive black hole. I mean, it perfectly predicts everything from Mercury's weird orbit to gravitational waves. The successes are undeniable. But you know, that context is exactly why the cracks we're about to discuss are so fascinating. Which brings us to section 2, in our very first massive structural crack, fault line 1, singularities. This is where we hit a concept called predictive self-destruction. Back in the 1960s, Roger Penrose and Stephen Hawking proved a set of theorems showing that general relativity actually mathematically proves its own equations become absolutely meaningless under certain conditions. Think about inside every black hole or at the origin of the universe, the Big Bang. The math says space-time curvature and density diverge to infinity. Now, an infinite quantity in physics usually means your theory has just broken down. General relativity is incredibly unique because it forces its own breakdown. Moving from the infinitely dense to the infinitely vast, we hit section 3, fault line 2, vacuum energy. Okay, to understand this one, we have to talk about a staggeringly huge number, 10 to the power of 120. That is a 1 followed by 120 zeros. This represents what is widely considered the worst quantitative mismatch in the entire history of physics. See, quantum field theory predicts that empty space should have a background vacuum energy. This would act just like Einstein's cosmological constant, pushing the universe apart. But when physicists calculate what that energy should be and then compare it to the cosmic acceleration we actually observe, the prediction is too big by a factor of 10 to the 120th power. It's just unfathomably off. And it actually gets weirder. Enter the coincidence problem. It is not just that the cosmological constant is bizarrely small, it's that it happens to perfectly match the current matter density of the universe right now, in our specific cosmic epoch. Since matter dilutes as the universe expands, but this constant stays exactly the same, this rough equality happening right when we exist to observe it is a massive coincidence. Critics call it fine-tuning. Ultimately, general relativity alone simply cannot explain this. It's a stark reminder that we are fundamentally in the dark about 95% of the universe's makeup. And that invisible 95% leads us straight into section 4, fault line 3, missing mass. So, general relativity relates space-time curvature to the matter that is present. But when astronomers apply the theory to galaxies using only the visible matter, it completely fails. This is the missing mass problem. In the 1970s, Vera Rubin measured how fast stars orbit in galaxies. Newton and Einstein's math said stars further out should orbit slower, but they didn't. The rotation curves stayed flat. To make the math work on galactic scales, we are forced to invent an invisible substance. We call it dark matter, and we see its undeniable gravitational effects, like in the bullet cluster where colliding galaxies show invisible mass cleanly separating from the visible gas. But here is the uncomfortable reality we have to face impartially. It's evidence without identity. We have overwhelming gravitational proof that something is out there, but for over 3 decades, direct detection particle experiments, massive setups like Lux Zeppelin and Xenon XT, scanning for these elusive particles, have come back entirely empty. The theory simply doesn't fit the sky without adding invisible matter, yet we still haven't physically found the matter.
Now, let's descend into the deepest foundational crack of all, Section 5, the quantum mechanics clash.
What we're looking at here is a literal mathematical war. On one side, general relativity treats spacetime as a smooth, continuous, deterministic geometric object. It's predictable. On the other side, quantum mechanics tells us the universe is inherently probabilistic, chaotic, fluctuating, and totally subject to uncertainty. When physicists try to mathematically combine them, treating gravity like the other quantum forces, the calculations just explode into unsolvable infinities. The math is mutually exclusive. And the ultimate battleground for these two Nobel-worthy theories? The black hole event horizon. In the 1970s, Stephen Hawking showed that black holes emit thermal radiation and slowly evaporate. But here's the catch. Thermal radiation carries no information. So if a black hole evaporates completely, the information about everything that ever fell into it is permanently destroyed, and that violates a core untouchable principle of quantum mechanics, that information cannot be destroyed. This is the famous unresolved information paradox. Our two greatest frameworks just can't both be exactly true. But don't despair. This is actually where it gets incredibly exciting. Section 6, probing the edges. Because these cracks, they aren't ultimate failures. Locating these exact fault lines is empowering because it provides us with a physical treasure map pointing straight to new physics. We have an incredible next generation of space missions actively targeting these cracks as we speak. LISA will launch to test strong field relativity using supermassive black holes. The Euclid and Roman space telescopes will probe the dark energy and dark matter fault lines through immense, sweeping cosmic surveys. And experiments like the microscope satellite are testing the absolute foundational assumptions of gravity to unprecedented precision. They know exactly where to look for the breakdown. So the big takeaway I want to leave you with today is this. General relativity is a spectacularly successful effective theory that has survived for over a century by being perfectly, provably incomplete. It tells us exactly where it falls apart. The real question for the next generation of physics isn't if Einstein's cathedral will crack, it's already cracking. The question is, what incredible new universe will we uncover when it finally breaks?